Hello and welcome. In this video, we're going to be talking about the inflection points as well as the concavity of a function. So let's get right into it. Let's start by doing concavity and understanding what it means. Basically, a concave up function looks something like this. This function is concave up for all x values, and a concave down function looks like this. So this is concave down for all x's. Let's think about what's happening here in terms of the gradient or f dash of x, because f dash of x is basically the gradient. So over here, the gradient was negative, so it was, let's say, -1. We know that this point is a stationary point, so the gradient here is 0. And over here, the gradient is a positive gradient, so the gradient here is 1. So what's happening to the gradient is going from -1 to 0 to 1 to 2 to whatever. So we know that the gradient is increasing. That means that f dash of x is increasing. And since f dash of x is increasing, the differentiation of that, which is f double dash of x, must be positive. So what I want you to know is that for a concave up function or a concave up interval, the second derivative of x is positive. And on the other hand, is the same idea for a concave down. So right here, we had a positive gradient. Let's say m was equaling to 1. Here, m was equal 0. And here we have a negative gradient, m equals -1. So as we can see from here, the gradient is going from 1, decreasing to 0, and then to -1. So the slope or the gradient or the first derivative is decreasing. And we know that when something is decreasing, its differentiation is going to be less than 0. So when the differentiation, the second derivative, is less than 0, that's when we say that the function is concave down. So these are the tests that we do to test if this at this x is the function concave up or down. Another thing, which is called the inflection point, this is the point where the second derivative is exactly 0. So when the second derivative is exactly 0, that means that at this point, the function is neither concave up nor concave down. However, it's called an inflection point. And I know that the concavity at this inflection point changes either from concave up to concave down or from concave down to concave up. So you can think of this inflection point as the point where change of concavity happens. So let's say we have a function that is totally concave up and then another function that is totally concave down. Let's say these two functions are joined onto one graph. So as you can see that at this point over here, up until this point, this function was concave up, and then after this point, function became concave down. So this point over here is called inflection point, and the f double dash of x at this point equals 0. F double dash of x on this whole interval is greater than 0, and f double dash of x on this interval is greater than 0. This is concave down interval, this is concave up, this is inflection. That's basically our topic 90% covered. So let's apply that with some examples. So the question will say, find the inflection point of the following functions and the intervals where f of x is concave up and concave down. So let's start with our first example over here. Let's say we have a function f of x equals 4x cubed plus 21x squared plus 36x minus 20. So this is our function, and we need to know what are the inflection points. So we know that inflection points happen when f double dash of x equals 0. So let's start by getting f double dash. In order to do that, we need to get f dash of x. This is going to be 4 times 3 is 12, and then x reduce the power by 1, x squared, plus 2 times 21 is 42, then this is going to be x plus 36. That's my first derivative. My second derivative is going to be the differentiation of the first derivative, which is differentiation of this expression. So it's going to equal 24x plus 42. And then let's set that to 0 and solve. So let's subtract 42 on both sides. So we're going to have 24x equals negative 42. We divide by 24. We divide by 24. This is going to give me an x of negative 1.75. So basically, this is my inflection point. This is the point where concavity change. So let's draw a number line, okay, indicating this point in the middle, x equals negative 1.75. And let's test the answers to the left of this point and to the right of this point. So to the left, we can take any value. Let's say x equals negative 2. And let's test it in our second derivative to see if the second derivative is going to be a negative value or a positive value. So f double dash of negative 2 is going to equal 24 times negative 2 plus 42. So this is going to give me an answer of negative 6. So basically f double dash on this interval is a negative, so it's less than 0. Let's test a point on the right of negative 1.75. So a very easy point is when x is 0. So we test it in the second derivative, f double dash of 0. So when I change x with 0, this is going to cancel, and I'm going to end up with a positive 42. So I know that my answer is 42, which is a positive number. So f double dash of 0 or of x on this interval is greater than 0. So we know that the function is concave down when f double dash of x is less than 0. So the interval where it's concave down is going to be from negative infinity up to negative 1.75. That's the interval where the second derivative is less than 0. And it's concave up in the interval where x is negative 1.75 until positive infinity. So this is my answer, and my inflection point is at x equal negative 1.75. If I want to find the exact point, I can substitute this x in the original function over here to give me the y, but this is not our concern now. Let's try another example. Let's say f of x let's say we have f of x equals to x e to the power of x. Again, we need to find the inflection point, so we need to find the second derivative. So in order to do that, we need to find the first derivative first. So this is a product rule over here. So I know from product rule, and by the way, I did a video on product rule. I will leave the link on the top right hand corner. Go check it out. Is going to be differentiation of the first. So differentiation of x is 1 times the second function, and then adding to that the first function normally, which is x, and then multiplying the differentiation of e power x. And I know that the differentiation of e power x is basically e power x. So this is going to be e power x. So this is my first derivative. My second derivative is going to equal, okay, differentiation of e power x is basically e power x plus differentiation of this again is going to be the same as this. So let's do it. So it's differentiation of the first, so 1 times the second function, which is e power x, adding to that differentiation of the first function, the first function normal times differentiation of the second function, which is e power x. So basically, I have an e power x plus an e power x, so it's going to equal 2e power x plus an x e power x. So now I need to equate this to 0 and solve for what x's are going to give me a value of 0. So I can see straight away that I can factorize an e power x from here. This is going to give me a 2 plus x times e power x. Divide e power x is basically x. So two answers I can have here when e power x is equal to 0, and I know that e power x is never going to be 0, so no solutions here. And the second answer is when 2 plus x equals 0, and I know that here x is equal to minus 2. So basically, this is my inflection point, the point where concavity changes. So let's draw our number line, and let's say here this is x equal -2, and let's test f double dash of x when it's on the right of -2. So I know that 0 is on the right of -2, so I can substitute 0 in f double dash of x. So f double dash of 0 is going to equal e power 0 times 2 plus 0. So I know that this is 1. So 1 times 2 plus 0, which is 2, so equal 2. So it's a positive answer. So I know that f double dash of x over here is positive. Let's test a negative answer. Let's say x is -4. So f double dash of -4 is going to equal e power -4 times 2 plus -4. So I know that e power anything is always a positive number. So here that's a positive number multiplying 2 minus 4 is basically -2. So -2 times a positive number is going to give me an answer that is less than 0. So I know in this interval f double dash of x is less than 0. So here is the interval where it's concave down. Here is the interval when it's concave up. So if I want to write that, I'm going to say concave down interval when x is from -infinity, which is over here, all the way up to -2. And then concave up is when x is from -2 all the way up to infinity. So this is my interval over here. Let's take another example. Okay. Let's say we have f of x equals -x power 4 plus 4x cubed minus 4x plus 1. Again, to find the inflection points, I will need the second derivative. So getting the first derivative first is going to equal -4x power 3 plus 12x squared minus 4. Getting the second derivative is going to be -12x squared plus 24x. And equating that to 0, straight away I can take out a -12x as a factor from here, and I will have -12x squared divide -12x, that will leave me with an x, and then 24x divide -12x is basically -2. So I have two solutions when -12x equals 0, and I know that will give me an x of 0, and when x minus 2 equals 0, and that will give me an x of 2. So these are my two inflection points. So right now I have two inflection points over here. So let's draw the number lines and put on our x's. So this is x equals 0. This over here is x equals 2. And let's test the second derivative in each interval. So let's start by testing an x in this interval. So let's say x is -1. So f double dash of -1 is going to equal -12 times -1 times -1 minus 2. So this is going to be +12 times -3, which is -36. So over here it's a negative value of f double dash of x, or it's a negative, it's less than 0. So it's concave down over here. Let's test a point over here. So between x equals 0 and x equals 2, I can take an x equals 1, and I will test that. So f double dash of 1 is going to equal -12 times 1 multiplying 1 minus 2. So that is a -12 multiplying 1 minus 2 is -1. So -12 times -1 is +12. So I know that over here f double dash of x is positive, so it's a concave up. And over here I can test x equals 3, so f double dash of 3 is going to be negative 12 times 3 times 3 minus 2. So this is going to be negative 36 times 1, which is negative 36. So again, this over here is a negative number, so it's concave down. So for the period or the interval where it's concave down is going to be x from negative infinity up to 0 and from x equals 2 up to positive infinity. This is the intervals where they are concave down. And when it's concave up, it's basically this interval here from x equals 0 to x equals 2. This is my answer for the intervals, and the inflection points are at x equals 0 and x equals 2. So let's take one more example over here. Let's say that we have a function f of x equals arctan or tan power negative 1 of x. So I know that the first derivative for arctan of x is basically equal to 1 over x squared plus 1. So the second derivative is going to equal, I can rewrite this as x squared plus 1 power negative 1, and I can use the chain rule to solve this question over here. So the differentiation of this is going to be the power times the coefficient, which is going to be minus 1, or basically minus, and then x squared plus 1, and we decrease the power by 1, so it's going to be minus 2, and then multiplying the differentiation of what's inside this function over here, and it's going to be 2x. So basically this is equal to negative 2x multiplying 1 over x squared plus 1 all to the power of 2. So I will equate this to 0 and try to see what values of x that can make my value 0. So inside this bracket over here, okay, it will never be 0. This can never be 0 because x squared is always positive, and then we're going to add 1. So this part over here, I can never get anything out of it, okay? And even if I got anything out of it, it's going to be 1 over 0, which is going to make my answer undefined. I'm going to have an asymptote. However, minus 2x, this I can say that if minus 2x equals 0, then the x that will cause that is basically x equals 0, because I'm going to divide negative 2 both sides. So this is going to be 0. So my inflection point is at x equals 0. Again, I will draw my number line. This is x equals 0. And I will test f double dash of x in this interval. So let's take an x of 1. So f double dash of 1 is going to equal negative 2 times 1 multiplying 1 over 1 squared plus 1 all to the second power. So this is going to be negative equal negative 2 multiplying 1 over 2 squared is basically 1 over 4. So this is going to give me a negative 1 over 2. So x, or the second derivative in this interval right here, is negative. So this is a concave down interval. Let's test an x over at this point. So let's say f double dash of negative 1. I know that negative 1 is in this interval. So it's going to be equal to minus 2 times negative 1 times 1 over minus 1 squared plus 1 all squared. So I know negative 2 is basically positive 2, and this over here is going to give me a positive number regardless. So it's going to be 1 over 1 squared is 1 plus 1, that's 2, power 2 is 4. So this is going to give me an answer of 1 over 2. So it's a positive answer. So here in this interval, f double dash of x is positive and it's concave up. Writing down the intervals. So when it's concave up, the interval is from negative infinity up to 0. And it's when it's concave down, the interval is from 0 to positive infinity. I hope this video helped. Please don't forget to leave a like, comment, and subscribe down below. If you have any questions or suggestions, feel free to write them down, and stay tuned for more. Thank you so much for watching.